Juno's original mission was to understand the origin and evolution of Jupiter in order to understand what governed how our solar system formed. It also extended its mission to explore the full Jovian system. The Juno spacecraft consists of a main body with a hexagonal two-deck structure with polar-mounted off-center spherical tanks. It uses a passive thermal design with heaters and louvers. The scientific sensors on board are individually heated and blanketed. Propulsion is provided by a bipropellant main engine for major maneuvers. It also has 12 monopropellant reaction control system thrusters for correction maneuvers.
For attitude control and determination, Juno uses 4 star trackers.
For telemetry, tracking, and control, it has a RAD 750 flight processor. It generates power using 3 solar arrays and uses 2 lithium-ion batteries for power and eclipse. Power distribution and drive unit provides controlled power distribution to the spacecraft. It uses the X-band for uplinking and downlinking and uses a dual band for gravity science. The payload consists of 29 sensors that make up the 9 science experiments on board. Power is generated using 3 solar arrays that consist of 11 solar panels and 1 mag boom. 2 55 amp-hour lithium-ion batteries that are tolerant of Jupiter's radiation environment are used for power during eclipse. Its total power output when it is still near Earth is about 14 kilowatts, which decreases down to 400 watts when it is near Jupiter. Due to the distance Jupiter is from the Sun, radiation degradation, and the power needs of the payloads, the solar panels were made to be 261 square feet, and the orbit was designed to have them in sunlight nearly all of the time. Additionally, the material in the solar panels picks up different kinds of light, which allows for better power generation than traditional solar panels. A power distribution and drive unit monitors and manages Juno's bus power, manages available solar array power, and provides controlled power distribution. For redundancy, the electrical power system is single fault tolerant so that if one component fails, that component is isolated and the workload is redistributed to the remaining working components. Additionally, the Pyro Initiator unit has a dual fault tolerant Polytechnic Initiator module.
Juno's communication needs to maintain reliable connection with Earth from deep space. To meet comms requirements, the spacecraft talks to Earth using high-frequency RF bands and has 5 different antennas for redundancy. Using high frequencies allows the signal from Juno to be transmitted with maximum amount of gain. X-band radio frequencies are used during orbital operations to communicate with Earth, while even shorter Ka-band frequencies are used during perijove passes with Jupiter to send scientific data. At its furthest ranges from Earth, Juno transmits data downlink at a minimum bitrate of 12 kilobits per second and 18 kilobits per second during its normal orbital operations. All of Juno's antennae are fed from a system of 2 traveling wave tube amplifiers, 5 waveguide transfer switches, and 2 diplexers. Juno mainly communicates information using its high gain antenna, but will use its medium gain and low gain antennas during safe modes or if there's something wrong with the high gain. These 4 out of 5 antennae are aligned with the spacecraft body's z-axis, but when these are out of alignment with Earth during maneuver burns, the low-gain toroidal antenna is used. All information collected and sent by Juno is received on Earth by the Deep Space Network at locations all around the globe.
Juno's thermal control system uses mostly passive thermal management with limited active heating. The spacecraft relies on thermal blankets, insulation, passive louvers, and the high-gain antenna acting as a heat shield. The louvers use bimetal actuator springs to automatically open and close based on temperature, allowing the spacecraft to regulate heat loss without electrical power. Active thermal control mainly comes from electrical heaters used on the external sensors and instruments. Juno experiences conditions ranging from near-Earth space to Jupiter orbit. As such, its design requires that it manages the thermal environment throughout its different mission phases. During cruise phases closer to the Sun, the high-gain antenna shields sensitive avionics from solar heating. Near Jupiter, heaters and insulation help retain heat in the much colder environment. The primary heat sources on board include the Sun, onboard heaters, and the heated propulsion module, while the main heat sink is deep space through radiative cooling by the louvers. To maintain thermal stability during extreme temperature changes, the louvers open to reject heat during hot conditions and close to retain heat during cold conditions. Heaters activate when instrument temperatures become too low, while insulation blankets and the electronics vault help reduce heat loss. Regarding redundancy and failure protection, Juno mainly relies on robust passive thermal systems rather than extensive redundancy. External instruments do have localized heaters, but overall the spacecraft depends on the reliability of its passive thermal design. In summary, Juno is a deep space spacecraft designed to operate in Jupiter's extreme environments. Its power system is built to operate far from the Sun using solar generation with stored energy for short interruptions. Communication is structured for reliable long-range data transmissions back to Earth with redundant links. The spacecraft is heavily radiation hardened to protect critical electronics. Thermal control is primarily passive, maintaining stable temperatures through insulation and radiative management.